So now what I want to do is look at how we can take motion in 2 or 3 dimensions and think about it. So the world is not one dimensional. This thing is 3 dimensional. And what we want to do is think about how we can think about objects moving not in 1 dimension, but in 2 or 3 dimensions. Now the trick to this whole problem, of course, is that we have to consider everything in vectors. And based on what you've learned about vectors and taking components, hopefully we can then treat motion in 2 and 3 dimensions, at least conceptually. So the big idea here is that displacement, velocity, and acceleration are all vectors. So the position, I can describe the position of this hawk flying down and then flying back up as a vector at any given time. And obviously that vector changes, which means there must be a velocity. So this velocity, of course, is a vector, right? And it changes. And it looks like, look at this diagram, mostly the velocity, the magnitude of the velocity, the speed remains the same, but the direction changes. So it accelerates. Over here, most of the acceleration, if you look at this arrow, the acceleration's mostly going downwards because the change in the velocity is mostly going downwards, right? So we have to consider different directions of velocity and acceleration. And remember that when we're dealing with vectors, we can take components, right, at right angles to each other, and we can treat each component separately. So let's look at this example of a hawk's motion. So this is the trajectory, the path that the hawk takes. Okay, and we're taking a 2-dimensional path for obvious reasons. So at different times, the position vector, the position can be described as a vector relative to the origin, okay? The reference point. Okay, and so there's a displacement here in a time delta t over here. This is the displacement. Now the displacement per unit time changes, right? So there's a velocity here. Your velocity changes. This is the velocity at this time. Velocity at this time is here. And so there must have been some sort of acceleration at any given time. And on average, therefore, if you think about it, at the beginning it's pointing downwards, and at the end it's pointing upwards. So the acceleration, at least on average, is going upwards on this hawk. So taking a longer length of the path, you can see that at each point you have a velocity, right, on the path, and an acceleration as the velocity changes along that path. Okay? So how do we solve problems like this? So we have a particular in constant acceleration or constant velocity. Now remember from 1D motion, we have developed various equations for solving for constant acceleration and constant velocity problems, right? We've got all of these. And there's nothing magical about the x direction. I can use these same equations along the y direction. And so when I was in school, I was taught the following. Res, horiz, res, vert. Confuses people. But res means resolve. So what I'm suggesting to you is that you consider, so just like we do for vector addition and subtraction, we separate the components and treat components separately. So we take the component in the x direction and the y direction, and we treat it as though they're 2 separate 1-dimensional problems. Okay? To illustrate the basic idea here, we're going to look at how we can solve a constant velocity problem in 2 dimensions. So let's draw a sketch of what's going on. So the swimmer can swim, okay, this way, right? If there's no current. So Vy here is 1.6 meters per second. But the swimmer also is being pushed downstream, which has an unknown velocity. We know that eventually, so this is t equals to 0, and at some point in time after some amount of time, a time t, it goes down somewhere here, which is 40 meters from here, and you also know it's 80, the river is 80 meters wide. So how long does it take the swimmer to swim across the river? Now, swimmer's swimming this way. So, but the key is, we don't care about whether the swimmer's motion up or downstream on the river. All we care about is the swimmer's motion across the river in the y direction. So this is constant velocity. So remember, constant velocity, we have x is equal to x naught plus vxt. There's nothing magical about the x direction, so I can just rewrite everything that's x into y. So I can say y is y naught plus vyt. So over here, we know that y at the end at time t is 80 meters is equal to y naught, the initial position, which is 0 meters, plus vy, which we know is 1.6 meters per second, times t. If I solve this, I find that t is 50 seconds. Now in this part, we know that it takes 50 seconds, right? We have the river. Let's draw it again. We know that at time t equals to 0, it's here. At sometime t is 50 seconds from the last part. It's somewhere down here. And so this is 80 meters. This is 40 meters. And you're trying to find the velocity, the speed of the current, the velocity in the x direction. And so let's think about this. If I use the equation x, this is constant velocity, so x is equal to x naught plus vx times t. The final position is 40 meters, initial is 0 meters, plus vx, which is what I'm trying to solve for. And then from the last part, because it reaches this point when it crosses the entire river. When the swimmer crosses the entire river, which is going to be 50 seconds. So that's the only thing that's linking the two together. What time has to be the same? The time component. The rest of it we treat separately. So if I solve this equation, I get Vx is equal to 0.8 meters per second.